Hi, my name is Ivan. I am from St. Petersburg State University, and today I will present our paper on methods for the efficient discovery of conditional functional dependencies with Desbordante. Conditional dependencies are a type of complex rules. In general, complex dependencies can be described as follows. For any pair of records, one condition implies another. The most well-known example of such rules is functional dependencies, which I will call FDs for short. An FD states that if two rows in a table match in some columns, then they also match in other columns. Complex dependencies are used to improve data quality, integrate data, optimize queries, and reverse engineering databases. In our work, we focus on conditional functional dependencies, which I will call CFD. Informally, this is an FD with a restricted scope. CFDs are particularly effective for data cleaning, data quality enhancement, and knowledge discovery from data. There are several ways to define a CFD. We will use the following definition. A CFD is a pair consisting of an embedded FD and pattern table that defines the scope of the FD. This table consists of the embedded FD attributes and one or more rows called patterns. Each pattern contains either a specific value from the domain of the corresponding attribute or a wildcard symbol corresponding to any value from the domain. A CFD is defined for a single relation instance and satisfied if for any pair of tuples and any pattern the following condition is true. If two tuples match the pattern of certain attributes, then they also match the pattern of the other attribute. For example, the CFD on the slide holds on the dataset, and its scope is all rows of the dataset that match the patterns. At the same time, the same FD does not hold over the entire dataset, because there exist rows that violate it. Most research in the field of CFDs focus on developing algorithms for automatic discovery. Since there are many ways to define CFDs, each discovery algorithm operates in its own manner. For example, some algorithms only look for a special case, constant CFDs, or patterns contain only constants without any wildcard symbols. Some algorithms consider only CFDs with a single pattern. More complex cases occur when CFD patterns can include predicates to specify more informative conditions. Algorithms for different definition of CFDs also usually use different search approaches. The most common method is traversing the lattice of potential CFDs and using additional methods for reduce the search space, such as closed item set mining or using a closure set. Algorithms can also be approximate, allowing a small margin of error in how precisely a CFD matches the dataset. For our research, we selected a state-of-the-art algorithm for discovering variable CFDs, CFD Finder. Its distinctive feature is it supports for multiple use cases and focus on the quality of CFD results. The algorithm also allows different types of condition in patterns, such as ranges of constants and negation. Its method is based on lattice traversal. This lattice is formed from the most generalized invalid FDs, which can be found using an algorithm for mining FDs called HiFD. The algorithm looks through all the candidates at the lattice levels, starting with the most specialized ones and moving on to the more general ones. For each candidate, it generates an approximate pattern table based on the given parameters. To do this, we use a greedy approach. We try to add the most appropriate pattern to the table, and in case of failure, we generate new patterns from it. If the pattern table can be constructed, the new candidates with a lower dimension are generated from the candidate and added to the lattice at lower levels. CFD Finder was originally part of Methonym, a research prototype written in Java that is no longer maintained. We re-implemented the algorithm in C++ with the possibility of optimization within the Desbordante platform. an open-source data profiler focused on performance. Later, we will compare the unoptimized metronome implementation with our version. Now I will describe the optimization we added. The main optimization is to revise the logic of the pattern table generation algorithm. We found that the original implementation allows duplicate patterns to be created, which significantly slowed it down. Furthermore, some resource-heavy computations, such as determining pattern color, are performed even when we already know that the pattern will not be suitable. We propose a batch processing approach in which lightweight color mask structure is used to filter out unnecessary patterns, and resource-heavy operations are performed only when we are confident that the pattern will be considered further. Implementing the proposed approach also allows us to reuse intermediate results from computing one pattern for computing a similar pattern with a different type of condition, which was not possible in the original implementation. Additionally, we implemented parallel lattice traversal. Pattern table generation for each candidate is independent, which is ideal for parallel computation. The speedup was also facilitated by replacing some data structures with more suitable and faster implementations. In our paper, we investigate the impact of our optimizations of the algorithm's execution time and memory usage. We also study the scalability properties of the algorithm. For your convenience, the research questions are displayed on the screen. To address the research questions, we conducted a series of experiments using three implementations: the original metronome implementation in Java, the optimized Desbordante implementation, and its multi-threaded version. The slide lists the system characteristics and datasets that we used in experiments. Experiments have shown that the optimized C++ version significantly outperforms the original Java implementation in both performance and memory consumption. It is worth noting that the Java version often shut down due to exceeding a HAO time limit. However, as can be seen from the number of discovered CFDs at the time of shutdown, the Java version was always far from complete. In contrast, the C++ versions were able to complete the work entirely and find significantly more CFDs in less time. The column scalability study showed that all implementations exhibit exponential growth in execution time. However, the C++ versions start this growth considerably later than the Java version, and the growth is smoother. Our versions process the full dataset in much less time, whereas Java reaches the time limit at only 16 columns. The graph especially shows how the multi-threaded version reduces the growth rate of execution time. The proposed optimizations also significantly improve the algorithm's ability to scale across rows. When changing the number of rows, the Java version exceeded the hourly time limit by 19,000 rows, while the total number of rows exceeded 150,000. Meanwhile, the C++ versions allow you to process the entire dataset in much less time than the set time limit. When evaluating scalability with respect to the number of threads used, one can observe that the algorithm speedup exhibits a logarithmic dependence on the number of threads, which is a favorable result. At the same time, the memory consumption dependence is very close to linear. The reason for this behavior can be explained by an implementation-specific feature. The peak memory usage occurs at the end of the program execution, so any memory overhead related to threads is overshadowed by the main memory consumer. In summary, our work helps to reduce the execution time and memory usage of one of the CFD detection methods. We also presented a more effective strategy for creating approximate pattern table for CFDs applicable to other algorithms as well. Thank you for your attention. Here's the list of references.